Yes, sir. Stream starting. Okay, Pongpon has already been there, right? Or when we get in, or change this, let's. It seems that no one joined. These it's already fine, but this one has to be changed to education. Education like this. Okay, no. Save. No, yes. Okay. Let me check the sound. Okay. We go to switch account. Another one. Yes. Yes. Zoom is right. Live is live. There is not live. First time. Go to this account, right? And we have to shift the sound. Okay. We didn't turn on this one yet. Okay, good morning everybody. Welcome you to SCI33206 in this is the section for M604, right? Okay, let me check the sound. Test 1, 2, 3. Test 1, 2, 3. Okay. Test 1, 2, 3. Okay. Sound doesn't go yet. Anyway. Test. Okay. All right. Test 1, 2, 3. Test 1, 2, 3. ใช้สิทธิ์ครับ and what happened hello test เสียงไม่ไปนะyour channel right test 1, 2, 3 ไม่ไปนะครับเดี๋ยวขออนุญาตรีสตาร์ทเครื่องแป๊บนึงนะครับI need to restart somehow ใช้สิทธิ์พิมพ์มาแล้วนะครับ capture ไว้ก่อนก็ได้นะครับเครื่องไม่รู้เป็นไรนะครับพักนี้ต้อง restart ครับ okay it's M604 right this one and it's better for me to restart the fasten and to that guy. Okay, yes. Yes, we will consider the nuclear physics, right? So we're gonna see what happened with nuclear physics in this lecture, but the iPad has a problem. I need to restart it. We arrive at the decay, right? Decay rates and so on in this chapter. And yes, we need to attain Okay, yeah. Our host is following meeting. First time, this one. Okay, the sound is come now. Okay, test 1, 2, 3. Test 1, 2, 3. เสียงก็ยังไม่มาอีกครับ Okay, we're gonna share. Test 1, 2, 3. อ๋อไม่ได้เปิดโอเค Test 1, 2, 3. เสียงไปแล้วหรือยังครับ Test 1, 2, 3. ครับโอเค Test มาแล้วนะครับเสียงมาแล้วอ้าวก็ยังอีก Test 1, 2, 3. Test 1, 2, 3. เอาพิมพ์กันมาแล้วนะครับโอเคlet's continue our lecture 1, 2, 3. อ้าวหายไปอีกแล้วโอเคผมปิดอันนี้แล้วกันTest เอามาแล้ว Okay. Yes. People are alive like that. Okay. We are alive at the decay rate. Okay, decay rate, which is the main stop to us. Yes. Last time we will take the limit right to this one. We're gonna take the limit of the decay rate, right, which is this one. Okay, without the absolute value, it's the rate of change of the nuclei per time, and you take the limit in the sense of calculus. Okay, in this way, in yes, delta is gonna be changed to the differential. It means the difference is very tiny, and we get the rate of change in calculus dn by dt equal to negative lambda, which is this equation. We take the limit on the right hand side here. On the left hand side of this equality, we get dn by dt. Let me capture your behavior. ทำไมอันนี้มันไม่ขึ้นผมก็ไม่ทราบนะแต่ถ้าเวอร์ชัน YouTube ธรรมดานี่มันขึ้น Okay. Anyway, let me see you in live. เกิดอะไรขึ้นไหมเอ่ยยังไม่ได้เปิดไลน์ YouTube. Yes, and the rate of change in the calculus sense is equal to minus lambda t, right? And you know that expression is in the Maxwell degree. It's called differential equations. Okay, actually there is also another type of equation which is called difference equation, and you're gonna see in the second mathematics subject in bachelor degree. Okay, the first year you would see is the differential equation, which is this one. Okay, dn by dt equal to minus lambda n Okay, and that's the differential equation. The way to solve, okay, this one. The way to solve this equation is that you have to move the same variable, which is the variable n, capital N here, to the same side of that equality. So you're gonna move capital N to the left hand side as the denominator in sorry, in the dt, right? dt, the small d to small d and t will appear on the right hand side as dt here. And yeah, you say you have the same variable appearing on the same side, on the left hand side. Okay, and now it's ready to solve this equation at the moment. ช่องนี้มีแต่คนเข้ามาที่ช่องนี้นะโอเคปัญญานัดตั้งแต่ปองพลมาโอเคช่องนี้ไม่มีใครนะโอเค yeah anyone else wanna join in Zoom no นะ no one wanna join in Zoom okay yes the way to solve this equation is that you put, because this is the differential equation, you take the integral. You know the integral symbol, right? This is the integral symbol. Okay, you just put this one into to both sides of equation 26. You're gonna get dn by n equal okay, and you just put negative out of the integral symbol, right? Oh, sorry. Even lambda, because lambda is a constant, is not, it doesn't depend on t, we get this one, right? And from the basic calculus tell you that basic calculus will tell you that here integration 1 by n dn is equal to the natural logarithm n plus c. Okay, this is the cn is the constant from the indefinite integral, right? You know indefinite integral, right? ภาษาไทยเรียกว่าปริพันธ์ไม่จำกัดเขต okay. And the next one is the integration of dt is going to be t plus c2, right? In integral of integration of fx dx without limit is called indefinite integral, right? And another type of integral is that you have the limit, which is called from a to b of fx dx. It's called definite. Okay, definite integral. Okay, and definite integral means it's the integral with limits. Okay, you get the actual value from that, but the result from indefinite integral, which is what we are considering here, what we have here, is the result without any number, because we need to substitute later. And yeah, on the left hand side we're gonna get the natural logarithm n, okay, because this is the ln n plus c1. You know ln, right? N is the natural logarithm or Napier based, okay, the logarithm function of Napier based for the variable x, okay, it depends on x. All right, yeah, that's the whole thing to us. And yes, the next one is the definite integral, but this is what we won't have here in this subject in physics, right? But at least you know, right? You need to substitute b and a, okay? But it's beyond, it's not the scope of this subject, right? Because we are talking about the physics, okay, not mathematics. Okay, we have a constant c here as the outcome because we combine c1 and c2, right? C1 appears on the left hand and c2 appears on the right hand side, and so on. And you move c1 to be involved with c2, you gotta get only c, which is a constant. Is what we don't know too, right? Yeah, because we don't know that, and we will try to find the remaining amount of the nuclei, which is the capital N here in terms of something else, right? The way to do that is we have to use the inverse function of the natural logarithm function, which is the exponential function, right? Yeah, and we're gonna take the exponential function to both sides of this equation. มีธินภัทรนะครับสุรปวีนะพิมพ์มาเพิ่มนะครับ KR and then we could now solve this equation by using the exponential function, right? N0 e once we take the exponential to both sides of this equation, let me write down it's in an empty page, right? You have e over ln n, right? Equal exponential lambda t plus c. Okay, it's too big, sorry for that. And from what you have ever heard before, the exponential of b plus c is going to be exponential b times exponential of z, right? And in the same way, you have the summation here. You, of course, on the left hand side, exponential ln n will remain n, all right? And exponential negative lambda t plus c will be actually exponential negative lambda t times exponential c. And let's say this is a constant, okay? This is the constant. It's a constant. We don't know, we could not do anything. We will find later because c is the unknown. Exponential of unknown is still unknown. Okay, that's the left hand side n. Okay, and on the right hand side we're gonna have exponential c and exponential negative lambda t, right? And of course you could see that with the view on the left hand side, n, the capital N, depends on t, right? Lambda is a constant, is a decay constant. We couldn't not do anything. Decay constant is always positive. Yes, n is a function of t and exponential c, exponential negative lambda t again. And once we take a look at time 0, we're gonna have n of time c, n of time 0, okay, n of time at 0 will be exponential c and exponential lambda and 0 right here. And as you know, any base of the power of 0 is gonna bring you to number 1 only, and that's why you have exponential c and number 1, right? And you're gonna get exponential c only. So and that's why we would have n at time 0 as the initial amount of the nuclei. Okay, so this one we will force it to be n0. So n0 is the initial amount of the nuclei. Okay, n is the amount of nuclei at time t at any time. Okay, yeah, that's different, and therefore we end up with this result in equation 28. Okay, the nuclei, the number of nuclei or the amount of nuclei at time t equal to n0, the initial amount of nuclei at time 0 at the beginning. Okay, at time t equals 0 times exponential of negative lambda t right here. Okay, the value of lambda for any isotope determines the rate at which the isotope will decay. Okay, how much that nuclei will disappear from the system, and that's the thing we will consider in this topic in decay rate. Right, decay rate is something about that. All right, when someone pay more attention in deeper way to that expression. Okay, yes, yeah, oh no, why I have to go back to that one. All right, ชวินชวับก็มาที่นี่ yes, no one here, right? Yes, the way to do is that they consider the new term, which is called half-life. Okay, half-life is the time that the nuclei disappear to the half amount of the initial state. Okay, and that's the meaning of the half-life. Half-life means the time. All right, and what next? The next thing is that we substitute okay at time equal to t1/2 is introduced or known as the half-life. Okay, half-life. Okay, the time that the nuclei remains only half the initial amount. And at that time, at this time, we are gonna see n at t equal t1/2 will be only 1/2 of n0. Okay, at this time, the number of nuclei remains only half of the initial amount, and we substitute this into this expression t equal t pi by t1/2, right? t1/2 and t1/2 here on the right hand side too. But at t1/2 we get 1/2 of n0 on the left hand side, this one, and we have here t n1/2, right? And we get this. And to solve this equation is quite simple, straightforward. You just cancel n0, the same thing, right, on both sides of the equation. And after that, you take the ln function to both sides. Okay, you get ln of 1/2, the inverse, because we're gonna want to okay, ln of exponential negative lambda t 1 by 2 t half, and lambda and t half is gonna move to the to be out of ln, right? And this will remain number 1. So you will get lambda t half equal to 1 by 2, right? And what we want is that we wanna find, and I don't understand why. Yeah, it's negative, so it's negative, right? So it's actually it's the same thing. Yeah. It's lambda is we take the natural logarithm, right? So it's ln of 2 here, 2n minus 1, and all right, it's the same thing, right? Yes, and yes, we get what is that? It's to the power of minus 1, and you take the logarithm function, right? You get, yes, it's ln 2 on the right hand side. Yes, you get negative ln 2, and you can cancel the negative side here. So in order to find ln 2, in order to find t1 half, or the half-life, you just move lambda to the right hand side and you get this equality here. Okay, and after leaving ln 2 in the calculator, you're gonna get 0.693. Okay, that's the approximation of ln 2, and yeah, it's quite simple for us, right, in the high school level, right? And the next thing is we could get right now t equal ln 2 by lambda, and from the initial expression, where is that? It's on page 37, right? 37. Okay, here. From the initial expression, 37. Right here. Yes, of course. Once we substitute t half ln 2 by lambda to this expression, you're gonna get. Let me open a new page. What is that? It's once you want to express anything in terms of time. Oh, sorry. T at any multiple time t half is gonna be n t half, right? N 0 exponential minus 1 by 2 and n t half, right? And what we know is that t half is ln 2 by lambda, right? Yeah, from this one, half-life is ln 2 by lambda. We're gonna substitute minus, okay, this is n, and here is ln 2 by lambda, right? In no, n0, this is lambda. It's not 1 by 2. This is lambda. Okay, you have lambda here, and of course you can cancel lambda to each other, and yes, it's gonna bring you to n0n still negative, right? It's exponential of n and ln 1 by 2, right here, and you get n0 exponential of ln 1 by 2 n, again power n, right? And inside that parenthesis is it will bring you to only 1 by 2, so you get n0 n 1 by 2 with the power of n. And that's why we arrive at this expression in equation 31. Okay, it's the amount of nuclei at a multiple time of half-life, and that's n0 1 by 2 with the power of n, and that's the thing we need to remember. It's remaining nuclei at multiple n of the half-life. Okay, the half-life. This is the expression for that. All right. Yeah, the remaining nuclei could be explained simply like this. N is the number of half-life, multiple time half-life you want to observe. All right. And yes, the number of half-life could be found also from any time you want to observe divided by the half-life, the time that the element or the nuclei disappear by half. The time scale of this decay process ranges from a small fraction of millisecond. Okay, very, very quick. Some nuclei would not stay so long. Okay, and they're gonna disappear quickly. And for some element like the elements on Earth, you would have like a billion years or something like that. Like some isotope of a big element like uranium or something like that. It's gonna remain only half for billion years, but we have already passed away. Okay. Yeah, we arrive at the first example of this type of problem, the half-life and decay rate, right? Half-life of radioactive nucleus. This is radon. Oh no, radium. Sorry, radium 226, and we are gonna see it later in the, I think in alpha decay, the first topic, the topic after this one. Okay, radium 226, that's the atomic weight or the mass number, and 88 is atomic number, the number of protons inside the nucleus of radium. The half-life, like I said before, it's take quite long. Half-life of radium is 1,600 years. My God. Or something like that. And yeah, sample initially contains at the beginning the number of nuclei for radium is, I don't know, 3 times 10 to 16. I don't know. It's 30,000 million. Okay. Yeah, nuclei. Oh, very, very large, right? Such nuclei determine the initial activity in Curies. So Curie is special one, right? The basic one is becquerel, Henri becquerel, the unit from Henri becquerel. Okay, the activity is activity is the decay rate. Actually, they want to find R, right? R in the absolute value, right? It's delta N by delta T. Okay, decay rate is something like that, and is equal to lambda and N, right? So they have provided the half-life, right, which is t half this variable. T half is 1,600 years, right? And you need to convert this one to second, right? Because once we compute something in physics, we need to make that quantity in SI scale. So T half could be expressed as 166,000. How many days a year do we have? We have 365 days per year, and we have how many hours per day do we have? We have 24 hours per day, right? And how many minutes do we have per hour? We have 60 minutes. You have to multiply. Oh, sorry for that. We need to multiply further and further. And how many seconds do we have each minute? So we have 60. We have 60 seconds per minute, right? So we have to multiply by 60 later. And that's the มีใครจะเข้าที่นี่ซูมไหมครับไม่มีนะครับโอเคไหมคนพิมพ์ชื่อก็ไม่มีแล้วครับโอเคthat's now return to our stuff that's the value you could get for the half-life in SI system. It's in second in sec, right? Yeah, quite a lot, right? And yeah, once you know T lambda, you could get you got T half, right? You could have lambda later from this relation from T half, which is half the period, half at the time that the nuclear remains half, right? Which is ln 2 by lambda, right? If you want to find lambda, you would get lambda equal ln 2 by T half, which is the half-life. And what they want to know is the activity or the decay rate, which is this one. So R will be what is that? N. The initial amount, which is the number of nuclei at the beginning. It's let me write down the expression first. It's ln 2 divided by T half, which is this number. Okay. You could write down here. I don't know how much, but yeah. Let me compute it somewhere else. Okay. Let me compute somewhere else so that we know that value. Okay. We're gonna compute somewhere else. Oh. Okay. What is that? 1600 times 365 times 24, right? And times 60 times 60, it's equal. Oh my god, very big. It's around 5 times 10. Oh, no. There are some digits after the decimal point. 0458 times 10 to 10, right? Quite a lot. And we use that number 50458 times 10 to 10. Okay, that's the half-life, right? Oh, I'm stupid. I need to write first the expression. This is the T half n times n, right? And once you substitute, it's gonna be ln 2. And divide that number 50458 times 10 to 10 and times n, which is the initial amount, 3 times 10 to 16, right? Yeah. Oh. Yeah. Now you could leave it into the calculator, right? That's the half-life. KRT half-life, something like that. And decay rate is going to be log of 2, right, divided by T half-life, and times the initial amount, which is 3E16, and yeah, it's equal to 4.1212 times 10 to 5. Okay, that's the nuclei per second, or decay per second, nuclei per sec, right? Is that correct? Oh no. It's not that. Where is 3.0? I don't understand why they have. Yeah, it's already correct. 3 times 10. Yes, you have to multiply by log 2 and 3 times 10 to 16, right? 3 times 10. T half-life is something like that. Yeah, it's it's already correct, 4.12. I'm stupid. But anyway, you need to convert it to Curie because they want to know this rate in Curie. 1 Curie is 3.7. You have to divide it by 3.7 E10, right? So it's gonna be not much. Okay, it's equal to 1.1138 times 10 to negative 5 Curie. Okay, Curie is denoted by Ci. And in appropriate scale, we're gonna say it's 0. It's 11.138 micro Curie. Okay, and that's the first quantity we could deliver to this problem. The next one is number of radium nuclei remaining after 4.8, 10 to 3. So it's, if you want to find the remaining amount, you just try to find the number of half-life, which is the multiple integer of the half-life. So you have T by T half-life, right? So it's, what is that? 4.8 times 10 to 10, right? To 3, only 1,000 here. Divided by 1.6 times 10 to 3. Please note that this is on the order of year together. Otherwise, you cannot go ahead with that. You need to have the quantities in the same scale or same unit. So n is a multiple integer. It's only number 3. And from equation 31, you could have n equal n0 of 1 by 2 times 3, right? On time n. With the power of n, once n is equal to 3, you're gonna get initial amount is 3 times 10 to 16, right? And here you have 1 by 2 and 3 is division by 8, right? Division by 8, 3, 16, 3E16 by 8 is going to be 3.75 times 10 to 15 nuclei. Okay, nuclei. And that's the second quantity. The third quantity is the activity at these later terms. So if the decay rate is lambda and n, right? So and you know that lambda is ln 2 by t half, right? And once you substitute back, you're gonna get rate at this time is gonna be ln 2, right? Ln 2 divided by half-life and n, right? And we substitute ln 2 into that expression. It's somehow 3 point blah 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 699 or something like that. And you get a half-life, which is this number in the SI system. It's 40458 458 times 1010. And the number of nuclei, which is at the moment, right, we get 3.75, 10 to 5, 10 to 15, and yeah, once you put it into the calculator, you're gonna get the result, right? T half-life is that in this is R, right? Yes, it's gonna be log of 2 times R and divided by T half-life, and you get 1. Oh, why is so small? Why? Rate is like that. Yes, it's already. Yeah, it's almost correct. N is 3.75, right? No. Rate is not that one anymore. Rate is this one. Oh no, the n, right? N is this one, and we need to multiply n th. So it's 5.1515 times 10 to 4, and that's the decay per second. But it's better if we express it in Curie, right? So is gonna be that number 5.1515 times 10 to 4 divided by the scaling by Curie, right? It's 3.7 times 10 to 10, and you're gonna get the result 3.7 E10. You get a result as 1.3923 times 10 to negative 6 Curie right now. And if you want to express it in micro scale, it's going to be simply 1.3923 micro Curie, like that. And that's you get the result as equation 35 right here. So now we finish the decay rate at the moment. We're gonna go to the next section, which is alpha decay. Okay, the M605 just finished last time. Now we start alpha decay. Alpha decay. Before we talk about the alpha decay, let's get into the detail. What is the alpha then in this scenario? Alpha is another name of the nucleus or nuclei of the nucleus or the nuclei of the nucleus or the nuclei of the helium-42. All right, you know that helium has two stable isotopes or stable nuclei. The first one is helium-4, which is what we are talking here about, the with what we are talking about here, the alpha particle. And for the next type of isotope, next type of stable isotope from helium is helium-3, but it's not what we are talking about right here. Okay, helium-42 without, oh my god, what happened? Sorry, hold on. สวัสดีครับวางไว้รปภข้างล่างเลยครับเท่าไหร่ครับครับไม่มีดิครับครับวางได้เลยครับครับฝากรปภไว้ข้างล่างครับครับสวัสดีครับ alright oh sorry for that, someone is trying to disturb me. Yes, the helium-42 is the main target to us, and yes, we will we won't consider the complete atom of the helium-42 because we are talking about the nuclear physics, right? We will talk, we will take pay attention to only the nucleus of this atom, right? So the next one is that the next one is the detail, right? Helium-42 with the ion with the superscript on the right hand side here, 2 plus means without electron, it's only the nucleus. Okay, let me draw it for you to better understand. Of course, we start from helium, right, which is the next atom after hydrogen. You have proton, you have neutron, you have neutron, you have proton. That's the nucleus. Okay, nucleus of helium-42, and of course in the complete helium atom, in the stable way, you have electron around the nucleus. It's move around like this, and that's the stable or the complete atom. But let's once someone throw energy to this atom, both electrons will go away from this nucleus because nucleus is more stable. It has good binding energy, right? Binding energy is what you have seen before. It's packed in a tight way, so they can't be separated from each other easily. So once without electron, we would have only proton and neutron and proton. And this nucleus is called helium-42 2 plus because 2 electrons have moved away from this nucleus. Okay, and this is what we are talking about here as alpha particle. All right, the next thing is 4, right? What is 4? 4 is the number of nucleons, you know, right? There are 4 particles here. And 2, what is 2? 2 is the number of 2 positive charges, which is 2 protons here. And helium-42 is the helium ion, actually, because it has no electron anymore, right? And the mass of the alpha particle is around, is approximately, okay? It's not exactly this value. Is not 4 atomic mass unit, right? You know, you denotes the atomic mass unit. It's not exactly 4 atomic mass unit per atom, but in SI scale, we could express the mass of the alpha particle, which consists of 2 protons and 2. You just approximately combine the masses of these 4 particles together, you're gonna get this value. But it's not exactly the same, okay? This is the actual value the physicists have observed 6.644 times 10 to negative 27, and that's the typical scale for the mass inside the nucleus, right? But Okay, we know the detail of the alpha particle in terms of nucleus of the helium-42 without electron. We know the mass in the SI scale or in the atomic mass unit, which is important once we want to convert the mass into energy from the Einstein relation. EMC square by Einstein, right? The next one is the general process of this atom. Okay, this equation could be valid to any atom, but it doesn't happen easily in nature for every atom. Okay, only the big nucleus. Okay, we start from the element Y, and it has atomic mass. The mass number, right? The number of nucleons in the nucleus as the A, and Z is the number of proton for that specific element. And this, okay, the left hand side is called the parent nucleus. It's a big nucleus, and it is disintegrated to a smaller one, which shows you here on the right hand side as the element X. Element X has the number of nucleons as A-4. What is the reason why we have A-4? Because we have to dedicate 4 nucleons for the alpha particle, which is the nucleus of helium-42 2+, and we have to dedicate we have to allocate 2 protons for the number of for the protons inside the nucleus of helium-42, like this one. We have to allocate 2 protons. Okay, separate 2 protons for the helium-42 or the alpha particle. So the number of atomic number will be reduced by 2 from this process, because 2 proton has been reserved for the helium-42 or the alpha particle, and 4 nucleons have been reserved to alpha nucleus, like this. Okay. And yeah, that's the whole process for general alpha decay. Okay. Next one is that we go to the specific process that could happen in nature. One of the famous alpha decay is given by the 2 elements, uranium and radium. Okay, uranium and radium is the two major element. Let's go to the table where is uranium and radium. Okay, radium is the first element. Okay, radium is right here. Okay, and you go back by 2 to have 2 protons smaller, which is the element radon. Okay, radon is the noble gas. It's stable. Okay, radon is stable. Radium is not stable. It's alkaline. So it's quite reactive. It's quite sensitive to any chemical process. In the next element, the bigger one, is uranium, which is 92 here. 92 is actinized, so it's gonna be reduced to thorium. But actually, molecularly say the thorium is gonna change to other element later. Okay, yeah, uranium will be disintegrated to thorium, and radium will be disintegrated to radon, which is a noble gas. It's quite stable. Oh, that's the 2 possible processes in nature. We start from uranium 238, okay, which is a kind of isotope in uranium nuclide, and the specific number for this uranium is 92. Okay, you cannot have any other numbers than 92. Otherwise, you're gonna get different element. Okay, and we have to allocate 2 protons to the next element, which is thorium. We have to allocate 4 nucleons to that alpha particle, and we have to allocate 4 nucleons for the alpha particle from radium to radon 226 to 222. We have to allocate 2 protons from radium to radon, which is from 88 to 86, we get alpha particle 2 right here. Okay, both processes could bring you to the generation of the alpha particle, right? Okay, the half-life of the uranium acetone is billion years. Okay, it's quite long. And the half-life of the radium is 1,600 years. Okay, it's not so long, right? Radium is what we have just considered in the previous example, right? Yeah. In terms of figure, you could see what time we need to stop at 50, right? We start from radium, like right here, 226 and 88. What does that mean? We have 88 protons, okay, 88p, and the remaining, which is 226 minus 88, which is 138. That's the number of neutrons. Okay, the number of neutron is larger, right? It's greater than the number of protons in radium nucleus. And as you know before, right, the bigger element, the bigger nucleus needs to have more neutrons, okay, to get the nuclear force, the attractive forces that try to combine subatomic particles to form up the nucleus. Okay, and this is the reason why we have 138 greater than 88. Okay, to get more nuclear force, the attractive forces. Okay, the big nucleus stay constant without any movement at the beginning. At the beginning is 0 meter per second, and after this integration process, it's the alpha decay process. You get smaller nucleus. Okay, it's a little bit smaller than 88. It's 86, and now the number of protons have changed. It means we have got a new element which is no longer radium, is rather called radon. Okay, and it's a big nucleus for the gas, which is the noble gas, is stable. And from that, we reduce the number of protons by 2 to form a smaller particle, which is our target here, the alpha particle or helium-42. 2 protons in this location, and 2 neutron to this location with 138 to 136. Okay, neutron reduced by 2 to form up the helium 42 particle of alpha particle. And if you measure the mass of this one and this one collectively, you would find that the mass of the initial nucleus of the radium is greater than the summation of the mass by radon and the mass by helium. And from the Einstein relation, okay, let me write down. Mass of radium is greater than mass of radon plus the mass of alpha particle. What does that mean? It means the excess mass, the mass that doesn't show in these 2 particles, will be converted to energy. And that relation, which let's say delta M, which is the MRA radium minus MRN plus M alpha. Delta M is converted to energy, and the relation here is going to be E equal M and 931.5 mega electron volt per atomic mass unit. Okay, you just use this Albert Einstein in terms of mega electron volt expression. Okay, oh no, this is delta M too. Okay, this is delta M. Okay, the excess mass is converted to energy, and the energy will be allocated to this two particles, and it depends on the momentum, right? The energy depends also on the momentum, and the momentum start from this process too, right? Because we don't have movement, there is no momentum right here. The combination of the momentum of these two particles should remain zero, as the same as the beginning, here. Okay, in figure 8, the speed of the alpha particle can be determined from the curvature of its trajectory. Okay, of course, you know that these two particles have no electron at all, and both will be a positive charge. And once you know, in the previous semester, if you let a charge like electron or any positive charge moving, right, and if you have the B field, right, which is the magnetic field, this is the real part of the tail of the arrow, or the magnetic field. B field is pointing into this plane, right, this Electron node, and once it moves, one electron goes in this area, is gonna move up or down. From the expression F equal Q V cross B, you know that V vector V is in this direction, and B is pointing into the plane of this Electron node. And from the right hand rule, you use the right hand rule, right? The force is gonna point up, right? The force is gonna point up. That's valid for the positive charge, but for electron, the induced force is gonna point down. But we don't have electron at all in this one. Let's consider the positive charge, which is alpha particle and the nucleus here. The force is gonna pointing up, and once it moves in this B field, it's gonna move in the circle way, because the force will be perpendicular all the time to the motion, right? So the physicists just measure the radius from the expression. From the expression, radius of the movement here will be R equal to mv by qb, right? The charge of that particle. And if you want to find V, it's going to be V equal R qb by m, okay, the mass of that particle. You could measure the radius, okay, by using ruler or any device. You could measure the charge of this one, okay, it's not difficult. How many electron missing will tell you how much charge you have, and the strength of the B field is what you can control. The mass of this particle is known from the mass number, right? So it's not difficult to find the speed at all. And from what the physics in their measurement, okay, they found that we consider only the alpha particle. We don't pay attention to the radon nucleus at all. The alpha particle has the velocity or the speed 1.5 times 10⁷. It's like 15 million meter per second. It's very, very, very high, right? And once you put it into the typical kinetic energy expression, is 1/2 mv square, right? 1/2 mv square. You're gonna get 1/2 here at the beginning, and the mass of the helium-42 is provided here in the SI scale. It's 6.644 blah blah blah. Okay, 82 is the uncertainty of the last two digits of 30. Okay, you just plus or minus, because in reality we have limited accuracy of measurement, so we could not find the accuracy at any deeper integer after the decimal point. So you can simply use 6.644, okay, 6.64 even, times 10 to negative 27. You can approximate this one, okay, it's very important. That's the scale of the mass. Okay, that's the mass of the alpha particle for any case, right? And the velocity is what they have found from the measurement here, which is 1.5, 15 million meter per second, and you take the square from the kinetic energy expression, E equal 1 by 2 mv square, right? And yes, you get 7.47 in 10 to negative 13 joule, is very, very tiny amount actually. So it's not considerable to our human scale, right? You cannot feel this energy because the particle is very tiny, but it's better to be significant or to be considerable in physics, in nuclear physics society, by converting the energy in the energy that we have seen before in the previous chapter in atomic physics, right? And that unit is electron volt. The way to do that is just to make the multiplication of that amount by the electron charge 1.610 to negative 19 joule, and you get the amount of energy in electron volt, which is still high. Okay, you have several order of that quantity. And yes, of course, you know that the people use the nuclear physics to make the nuclear bomb and so on, because nuclear process provide much more energy than electron scale or atomic scale. Okay, you get more energy from the nuclear scale rather than the atomic scale. Oh, what happened? โทษครับมาอีกแล้วครับ sorry ฮัลโหลครับครับเอาฝากโลพอไว้ข้างล่างเลยครับ G ครับG ครับตรงเลยเซเว่นมาตึกใหญ่ๆสีเทาแดงครับติดถนนครับใช่เลยเซเว่นพอเจอทางตัน3 แยกเลี้ยวขวาก็จอดเลยครับนั่นตึกนั้นแหละครับฝากรปภตรงตึกนั้นครับฝากไว้ได้เที่ยงได้ไม่เป็นไรครับครับขอบคุณครับ Okay, sorry for that. Yes, the energy here in nuclear scale is around 10 million. Okay, greater than the energy in electron orbit, right? In the orbit of the electron, because we consider something inside the atom. The way to do that is you just divide this quantity by 1 million, okay, and the decimal point is gonna move 6 times, and you receive you get 4.66, and it's mega right now. Okay, you have the prefix unit instead of conventional electron volt. Okay, electron volt is suitable for electron orbit scale, but for nucleus it's gonna be in I don't know, it's in mega electron volt. Okay, it's gonna be in mega electron volt. Yeah, that's the kinetic energy from the alpha particle, right? You could see that it's stronger, right? It's stronger than electron. Okay, yeah. We could not do, yeah, and this is the clever thing for the people that try to disturb someone else by building the atomic bomb or nuclear bomb from this process. Okay, yeah, but in a good way, human also uses this process, for example, to produce electricity, and that could be useful to everyone, right? Not only nuclear bomb, right? We can also apply this process to generate electricity. We could use alpha particle for other purpose, for scanning purpose, for any other application. Okay, we study only pure science here. Yeah, if you go into the detail of physics, there is no kinetic energy at the beginning. Okay, in this let's consider ขออนุญาตเลยสัก3 นาทีนะครับเพราะว่าเราสตาร์ทช้านะครับเนื่องจากผมติดเรื่องอะไรเรื่องอิเล็กทรอนิกส์อุปกรณ์ครับ radon is 226 right there is no kinetic energy at all there is no momentum at the beginning because there is no movement of the radium nucleus before decay okay and after decay both will move from each other right you know the reason why they move from each other because some of the mass which is the excess mass is converted to the energy and the way to compute the amount of the energy is delta M times the 931.5 mega electron volt per atomic mass unit if you don't know why we have 931 you have to go back several pages of this lecture right we have already shown we get EMC square in terms of a simpler formula 931.5 mega electron volt per atomic mass unit okay you just compute the excess mass in atomic mass unit you get the energy in mega electron volt okay and that energy will be distributed to both particles when both particles have the energy they are going to move right once they move there will be again two quantities the first one each quantity will have two things the first quantity is there will be kinetic energy right Ke is kinetic energy there will be momentum because there is movement velocity there will be kinetic energy there will be momentum also here all right yes but in physics we have the principle of conservation right like energy conservation right and the momentum conservation something like that and now we arrive at this problem we will talk about that later because the time is over right now I need to let you have a break right ก็วันนี้ก็ต้องจบเพียงเท่านี้นะขออนุญาตเลยสัก5 นาทีเพราะว่าเสียเวลาเซตเครื่องครับผมมาช้าวันนี้โอเคครับวันนี้ก็คงจบไว้เพียงเท่านี้แล้วก็การบ้านนะครับการบ้านก็เป็นเรื่อง decay rate นะครับhomework I don't know the 9 homework for M604 right it's something about decay rates okay homework of M604 is right let me write down the 9 homework for M604 is the decay rate you have to do something about decay rate นะครับขออนุญาตเก็บงานคุณนิดนึงครับเพราะว่าจะได้เก็บเป็นคะแนนทำเป็นคะแนนเก็บให้คุณนะครับถ้ามันไม่ทำกันบ้านเลยคือผมก็ชอบแหละ ตอนผมเรียนก็ไม่ชอบมีกันบ้านแต่ว่าไม่รู้จะไปเก็บคะแนนให้คุณยังไงครับให้คุณมานั่งท่องสูตรฟิสิกส์ให้ฟังเหรอหรือว่ายังไงผมก็ไม่รู้นะครับเอาเป็นการบ้านแล้วกันเนาะเพื่อวัดความเข้าใจนะครับ so do any problem about decay rates or anything with the half life and so on like what I have shown you here okay ก็พบกันวันพุธหน้านะครับ if you have any question just let me know okay see you next week บ๊ายบายครับสวัสดีครับit's subversion right subversion is existing only here let's see with มีพัดปองพลนะธนัท Okay, now is the section for now is the section for M605, right? Okay, it's the time for M605 section. In here is the homework for M604, and we finish at this one. In here is 1401 22 for 604. Now it's time for M605, right? But no one has arrived yet. I'm gonna check whether you wanna join here in this in the Zoom or not, right? Okay, that's the chassis. Anyone from M605? Not yet, right? Okay. Seems to not work perfectly. Come on. No. Seem to not work properly. Okay. All right. This is the section for HDR or something like that too, right? HDR. Okay. Dynamic range. All right. Yes. We arrive at the M605 section, but no one from M605 has start typing. นะครับ605มากันแล้วหรือยังครับ605มาแล้วหรือยัง M605 January 14 Streamlabs, so it's correct, this one. M605 สุรปวีณมาแล้วนะครับสุรปวีณ okay. Yes, it's สุรปวีณ right, but why I couldn't see you? Suankularb Wittayalai appears here already. Okay, now let's start the M605 because I'm not sure whether you attend it or not. Otherwise, I'm gonna speak without you, and that might be a problem. Okay, yes. What else? This way. Okay. Yes, welcome. Good morning, everyone. Welcome you to SCI33206, which is physics number 5. Okay. This is the section for M605 and only Supavit. See that? Supavit ดึงข้อมูลกลับคืออะไรเลย Okay. Yes, let's open. My God, this is the file for M605. Okay, we arrive at the alpha decay result right alpha decay ไปอีกช่องนึงนะครับ super width ไม่เป็นไรwe are at the end of the we are at the end of the alpha decay and the M604 just start this one right yeah, the observed energy of alpha particles are discrete because they have certain power spectrum, right? Not every certain power. Okay, in pretty non-matter. In next one is the distribution of alpha particle energies in the typical alpha decay. So the power, the kinetic energy have a discrete value, and once we observe each particle, right, and they observe the kinetic energy on the X scale, and yeah, each value of the kinetic energy have multiple number of alpha particles. Okay, and it's not continuous. Okay, that's the distinct feature. Okay, it's a unique feature of the alpha decay. Okay, alpha decay come in discrete amounts of energies because the two daughter particles which are these two things radon and alpha particle have momenta with equal magnitude. Okay, the absolute value of the momentum, the absolute value of momenta for both particles are the same, but the direction is different. That's why they are negative version of each other. And then the next one is and are each composed of a fixed number of nucleons in yeah, they don't have any other examples of nuclei, right? So they have only radon and helium-42. That's why they have fixed the numbers of nucleons. And now we arrive at the next type of decay, which is called beta decay. Okay, beta decay is the decay that is more sophisticated than the alpha decay. Okay, it's something about newer particle. It's more is newer process that human has observed. Okay, human has observed in recent year, in 20th century, around 120 years ago. The scientists start to observe some particle and some processes. And a beta particle, which is known as, is denoted by the letter beta, is known as electron. Okay, electron is actually the particle that we were familiar with, right? And sometimes it's known as beta once it moves with momentum with what is that? Momentum and kinetic energy. So we would say it's beta particle. Okay, if just stay without any movement, we would say it's solely electron, right? Okay. Yeah, the emission of electrons from nucleus is surprising because in all previous discussions, we start that nucleus is composed of protons and neutrons only. That's the basic knowledge. Everyone agree with that. But for some scenario, once the physicists discovers something new, they found that not only protons and neutrons could be found in the nucleus of any atom. Because in some process, the neutron, okay, could be converted to proton. Because neutron is neutral, right? It has no charge. The word neutron comes from the word without charge. Okay, it's neutral. It's in the middle. It's neither positive nor negative. So neutron is in the middle. And from this knowledge, for some process, some scenario, neutron, which is denoted by the blue one here, okay, could be transform itself to proton. And maybe you have ever seen the structure of the neutron before, right? Neutron and proton are made of up quark and down quarks, right? Two of them are down quark or two of them are up quark. Two up quarks means it's neutron, right? And the quark can change itself. So once the quark changes itself, the neutron will be converted themselves automatically from the state of neutron to be proton. And once it's generate the positive charge, they're gonna split also the negative charge, and that negative charge is called electron. Okay, at the beginning, okay, and from what we could observe from the nucleus is that for a certain time the nucleus change itself and we get a new element, the same atom transform itself to a new element, and they just throw away electron from the nucleus. It's not the electron that move around the nucleus, so it's the electron emerges from the nucleus. Okay, at the beginning the people believed that the neutron could generate only proton and electron, but recently when the scientists go further into the detail, they found that the mass are not balanced. Okay, the mass from the first state to the second state are not equal to each other, so they believe that there should be another particle, and that particle is known as electron neutrino or electron antineutrino. Okay, depends on which process. But for a neutron to be proton, we're gonna get electron antineutrino. But at the beginning, they say electron neutrino. Right? But actually, once the time goes by, they say electron antineutrino. The idea will come later. Okay, why they call electron antineutrino. Okay, an emission of electron from the nucleus could start from this one, and once you get the electron movement, okay, moving out of the nucleus or even out of that atom, okay, electron may have high energy because once the neutron convert somehow from this process, they're gonna release also the energy, and then the energy will be distributed, to these two particles. And once electron receive the energy, it's gonna move with high speed, and the particle here, electron with high speed, is known as beta particle. Okay, this one is known as beta particle or beta decay. Okay, so it's a state of changing neutron to proton. The emission of a beta particle is caused by the transformation of the neutron. Okay, neutron is denoted by N01. Okay, there is no proton, but there is one nucleon inside the nucleus. This is the nucleus notation or chemical notation in the nucleus into a proton. Okay, proton is denoted by P11, right? P11 because we have one proton, okay, at the lower left subscription, and one nucleon. Okay, there is no neutron. That's why the number at the lower position and the upper position are the same. And electron too, right? Electron. But that's the beginning state. Okay, the actual state is that there should be also electron neutrino or electron antineutrino. At the beginning of such type of investigation, they have only what is that? The neutron to be separated into proton and electron, right? A free neutron decays into a proton and electron, okay, with an average lifetime about 15 minutes, okay. Neutron has only lifetime around 15 minutes. It's going to be converted to proton and electron. To distinguish it from another particle, the positron, okay, that emitted particle today is called beta minus particle. So this one is called beta minus because it has a negative charge. So it's electron, simply electron. But because there is another type of beta decay too, that's the that's the positron. Okay, to differentiate this process from the positron, we're gonna say this is beta minus because it's involved with electron and one electron, right? It's negative charge, so we call beta minus with the positive on the right hand side, okay, on the superscript of the beta letter. Okay, it's called beta minus particle, and beta minus decay usually happens when does it happen? When the nucleus has too many neutrons, right? Or it's called the nucleus is neutron rich, okay, it's full of neutron. Okay, of course, we know at the beginning of this chapter that in order to make the system stable, the nucleus needs to have more neutron. But once they collect more too many neutrons, it's not good at all, right? And they have to convert neutron to proton somehow. And once they convert neutron to proton, they got a new element, new type of element. Okay, yes. When the neutron to proton ratio, okay, n by z, you know that n is the number of neutron, which is a minus z, right? Is too great for stability. Then the nature just convert neutron to proton by using this process. Okay, and we get electron out of the nucleus, and electron with high energy is gonna move out of the nucleus, right? And we get the beta minus particle, which is actually electron with high energy. Okay, the generic process of negative beta decay is given in terms of isotope balanced by, okay, it's different from alpha decay, right? Alpha decay start with AY, right? In alpha decay, you start with AY and Z2. This is the parent nucleus. This one is also parent nucleus. But no, this is not. It's not called parent nucleus because it's not a big one, right? And it just changes to another element which has one more proton, and the number of nucleon is the same because once the neutron is converted to the proton, they just still stay inside. It just stay inside the nucleus. So the number of nucleon inside the nucleus remain the same, but the number of protons has changed. Okay, the atomic number has changes. Once the atomic number changes, we have also the new. We need to write a new letter for this element because it's not the same element at all, not element Y at all. It's gonna be the new element. Let's say it's X element. And after that, we get electron, and electron with this energy, high energy, might be called beta minus particle, right? Beta with the superscript negative, right? And yes, of course, the number of proton is in the opposite way. There is the opposite way of proton is negative one, right? There is no nucleus, okay, zero nucleon here. Unlike the alpha particle, alpha process just split the bigger nuclei to smaller nuclei together with the alpha helium-42 nucleus, right? Yeah, but this one just change only the element and we get a tiny particle which is electron, right? That's the difference between beta decay. This is called beta minus decay process. Note that in the daughter nucleus, which is this one, X, the daughter, this is the parent nucleus. N decreases by 1, of course. N has to be reduced by 1 because the neutron transform itself to proton. There is no longer 1 neutron in this process, in that nucleus, right? Z increases by 1 because we got additional proton inside the nucleus here, so we get one more proton, so Z is going to increase it by 1, and A remains the same because the blue has to change itself to the red one. Okay, but the number of particles in this piece will still remain the same. Okay, so our typical beta decay event is given by the isotope balance. For example, it's carbon 14. Carbon 14 is a kind of, is an example for the beta decay process that you would be able to observe in equation 55. How does that work? Okay, of course, neutron is converted to proton, right? From 6 proton, we're going to have 7 protons. And what is that? Let's get back to the element in chemistry, element table of element in chemistry. 6 elements are 6 pieces of proton. 6 proton correspond to carbon, right? And one of the neutron inside the nucleus of carbon changes itself to be proton. Once we have one more proton, we're gonna go to the next element, which is nitrogen. Right now is non-metal too. Okay, carbon has converted himself to nitrogen, okay, the new element, but the remaining thing is that they also emit according to this process. Neutron is converted to proton, okay, but it still stay inside here. And during this process, they just produce also electron, okay, and with energy, electron is gonna moving out of the carbon nucleus, and we get now the nucleus of nitrogen plus electron with movement, with energy. Okay, beta minus is that thing. Okay, now let's move to another type of beta. Okay, in beta decay we have two kinds of beta decay. The first one is beta minus, and the second one is beta positive, beta plus. Okay, you can say also beta positive decay is the second type of beta decay. Okay, it's in the opposite way. Okay, in beta minus process, the neutron is converted to proton and to together with the electron. But for beta positive, beta plus decay, proton is converted to เชิญครับ ฮัลโหล
ดีครับ
ครับ
สอนอยู่ป่ะ
สอนอยู่ครับอาจารย์
ฝากลงคะแนนเสียงให้หน่อยนะ
อ๋อครับกำลังสอนอยู่ครับอาจารย์ขอบคุณyes, beta plus decay process is in the opposite way. The proton is converted to neutron. Okay, and let's see that what happened. Beta, or how or when the beta positive or plus process is gonna take place. Once the neutron to proton ratio is too small, okay, we need more protons. Oh, sorry. We need more neutron, okay, because now the nucleus is not stable. There is no enough attractive forces. There is no enough attractive force. There is no enough nuclear force for stability in the nucleus. So we would the nature will try to convert the proton to be neutron. Okay, and that's the reason. Okay, the origin of this process, the reason, right? When does this process is gonna take place? Once the nucleus is proton rich. Proton rich, what does that mean? It's full of proton. Okay, and you know that once the nucleus has too many protons, there will be too many Coulomb repulsive forces, right? The repulsive forces caused by Coulomb force, and that will make the nuclei or nucleus non-stable, and the nature will try to convert the proton to be neutron. Okay, they don't ask for any additional neutron. They just convert their elements inside their nucleon inside the nucleus to be another type. Okay, and that process is called beta or positive beta decay, right? Or beta plus particle. Why is the same way, right? We have y is that right to be something with lower amounts of proton with z minus 1, and now we change the element to x and the number of nucleon is a, and the outcome is beta plus, right? Beta plus is something like electron. Okay, it's the mass is the same as electron, but it doesn't have negative charge, but rather positive charge, and that's called positron. You may have ever seen positron, right? You may have ever seen positron in the where is that? The positron in standard table of elementary particle, right? Standard model of the elementary particles in physics. Yeah, and that's the positron, right? With the same amount of electron and with the opposite charge, exactly the same charge, but in a positive way. Okay, note that in the daughter nucleus, in this equation, right, in the beta plus process or positive beta decay, and increases by 1 because 1 neutron is converted to proton. Okay, at the beginning they believe that there will be only two particles, like the neutron and the positron, right? But it's not the case. Okay, if once they go further in terms of energy conservation, there should be another particle. Okay, and we will talk about that later. It increases by 1 because the number of protons increases by 1 and Z decreases by 1. It increases by 1 because proton has been converted to neutron, right? Z decreases by 1 because the number 1 proton has been reduced from the system. Okay, it just converted to neutron. Okay, there will be no one proton is missing, right? So it remains the same. Of course, the particles stay inside the nucleus will be the same. Just change the type from the blue to the red, from the red to the blue. So the number of nucleon inside the nucleus will be the same. In a magnetic field, beta particle can be identified. Okay, as I told you, when we have any positive particle, and if we have the B field, we can apply the right hand rule, right, to get the force direction. And once we get the force direction, that particle will move in a circular way. Beta particle can be identified, and their speed can be measured by the curvature of that part. Okay, let me write down again. I mean, if you have beta 0, 1 plus, which is the positron, when it moves like this, and if you have B like this, this is the B field, right? You can, of course, this is the vector of B, this is the vector of velocity of the positron. You would curl or rotate your forefinger and you will get the outcome which is the force in this direction. Okay, and yes, you know, right? F is Q V cross B, right? Yes, the force will be pointing up in this. Will point up in this direction from V to B, right? This is the rail, the rear part of the arrow, or the tail of this arrow. Okay, the magnetic field is pointing into this plane. You get F pointing upward, right? And the beta particle will move like this in a circle way. Okay, they're gonna move in a circular way, and you just measure the radius. From the radius, once you know the magnetic field strength, you know the amplitude of the magnetic field strength, you know the radius from the measurement, you know the charge of this particle, which is only 1.6 10 to negative 19 coulomb, right? And you know what else? You know the mass, right? Which is the same mass of electron. And yeah, you could get the velocity or the speed. That speed can be measured by measuring the curvature of their path. Okay, just measure the radius in this circle. The speeds range up to 0.995 of the speed of the light. Oh, it's very, very high. Okay, you know that electron is quite tinier than the alpha particle, than the helium-42. Helium-42 is a nucleus of one element, right? And once you go to you get a smaller particle like proton or electron. Once it absorbs the energy, they're gonna move very, very fast, and some of them could be captured on the almost the same scale as the speed of the light, which is 0.9995, which lies in the extreme relativistic range. You know relativistic theory, right? We need to use different theory in order to compare the momentum and so on, right? It's a little bit complicated than the classical momentum, PMV, right? We have to use the relative speed too. Okay, now we arrive at the first example about the alpha particle. Oh, sorry, beta decay. Beta decay. So now we will consider this problem. We will take a look at this problem. Okay, we consider the case of the carbon, right, which is equation 56, right? Equation 56, carbon 14 and 6 is decomposed into nitrogen. This is the case when neutron is converted to proton, right? We have one more proton, right? We have the same nucleon 14. Okay, and we have the electron, right, which is 0 minus 1, right? Negative charge. Oh, it's ugly, it's not beta. Okay, okay, it's beta, right? 0, 1, 2. Minus 1 and beta. All right. The beta positive decay usually take place, right, when we have too many neutrons, right? And what they have provided is that the mass of the carbon here is equal to 14.003242 atomic mass units, and the mass of the nitrogen from this one is 14.2, right? 14.003242 0.074 atomic mass unit. Right, and yeah, what is the what is the mass of electron? Mass of electron in atomic mass unit. Where is that? We have to get back to the origin of this chapter. Mass of electron. Mass of electron. Where is that? Here. The mass of electron in terms of atomic mass unit is very, very small, 0.0000548 or something, 49, okay, atomic mass unit. Okay, 49, you can see. Okay, that's the amount of the mass of electron in atomic mass unit. Okay, we're going to use the unit U so that we can convert it to energy easily. Right, and this is the theory. Okay, this is the theory in what is calculate the released energy of this beta negative decay, beta minus decay. So what is released energy, liberated energy, something like that. Okay, we have to compute the released energy from this process, right? And of course, the way to do that is the following. You have to convert the excess mass by 931.5 MeV per atomic mass unit, right? To delta M to E, right? E released or liberated energy as one. Okay, before that, we have to find delta M, the excess mass. The excess mass, what is that? It's the difference between the mass M604&M605 minus the mass on the right hand side of this process, which is the mass of neutron, nitrogen, plus the mass of electron, right? So the first term is 14.003242 minus two things. The first one 14.003074 in plus the third term, which is 0.000549, and that's the result, right? We just leave it into the calculator. Where's the calculator? Not here. Calculator. Okay, let's talk about a calculator. Okay, 14 point. Okay, delta M, right? Oh my god. Delta M. Oh, what happened? Keyboard. Delta M equal 14.000342 minus the summation of two things, 14.003074 plus 0.000549. That's the mass of electron, and you get, oh, why? 00307 003242 Why? The mass of that thing. Oh, okay. Okay. We assume that. Okay, we don't need to add the mass of electron at all. Okay, we assume that we use this value for the mass of the atom that is perfect. Okay, it is not in the ionizing state, so it's only the difference between those two values. Okay, the mass of carbon and mass of neutron only. So it's 14.003242 minus 14.003074, right? And you make the subtraction, you get any number. It's like a 0.0002. Oh no, not 2. It's 1, 6, 8. Okay, that's atomic mass unit. And after that, you convert this one. Energy equal delta M times 931.5 mega electron volt per unit. Okay, you just multiply it 0.00168 times 931.5, and you get 0.1564920 mega electron volt. That's the energy for this process, right? And that's the energy after the decomposition of the carbon to be nitrogen, right? Now let's move to the next one. Okay, that's the released energy. It's taken from, this one is taken from the book number 1, example 29.4, but this one is taken from the exercise 29.4. It's not the story about carbon and nitrogen. It's rather K. What is that? K. Potassium, right? And calcium, right? And calcium. Now we arrive at this story, right? Let's consider the one of the beta decay processes, which is something about potassium and calcium. You have K. What is K? K4019. K4019 is decomposed to calcium 4020 and plus beta 0 minus 1 and minus, right? Because that the emerging electron, right? It needs to have the negative charge on that, right? It's electron is when together with speed we call beta particle, right? Yeah, where is potassium? We may go to the chemistry table of element, right? Potassium, right? 19, right? 19 is here. Okay. Neutron is converted to proton, right? So we would have one more proton. And once the number of protons, which is atomic number, changes, by 1, okay, in the opposite way, in the positive way, we would get calcium from 19 to 20, right? We have one more proton, which is the result from neutron conversion. We get calcium, but they didn't say the number of nucleons, which is the mass number or the atomic weight here. They just simply say the number of protons, which correspond to the atomic number, okay, from potassium to calcium. It's close to each other, and you could see also carbon to nitrogen is close to each other, right? That's the beta process. Okay, we get potassium 40 and calcium 40, right? But we have one more proton. We get a new element. Okay. Now we will talk about the released energy, right? You know that the mass of the carbon 40-19 is given by 39.963999 atomic mass unit, and mass of calcium is 39.926591, right, atomic mass unit. And once you make the subtraction, you're gonna get the excess mass, right? Excess mass is mass of the calcium minus or subtracted by mass, or mass of potassium subtracted by mass of the calcium, and mass of potassium. Once you make the subtraction, right, you can look at the difference by i's here. This is number 8. This is number 0, this is number 4, this is number 1, and you have 2 0 here. And that's the atomic mass unit, the unit for the excess mass. Now it's time to compute the released energy, or liberated energy. You could say it's delta M times 931.5 mega electron volt per unit. Okay. Per atomic mass unit, and that's the factor we could convert. It came from EMC square, right? EMC square, mass of particle and so on, right? Yeah, if we use this number in we would get, we arrive at approximately 1.3115520 mega electron volts. Okay, that's the released energy from this process, from the potassium to be potassium to be calcium, right? Yeah. From potassium to be calcium. Now we finish it, and we will talk about the detail a little bit from the beta minus decay in 55. Yeah, we have calculated from theory, but we are not sure whether this number is valid or not. Right? That's what only the prediction from what we could expect, right? But we are not sure whether it's correct or not. And the way to be sure is the following: the scientists or the physicists go into the detail. Went into the detail. They assume that if there were only beta minus particle or electron and the recalling nucleus, the nucleus that changes itself, okay, from the mother nucleus for the parent nucleus Y, the conservation of momentum energy would require to have definite energy, right? Once we think about the classical physics, the momentum and energy should be conserved, right? From this process, from the alpha, from the beta process, from whether it's from 55 or 57, okay, the momentum and energy should be conserved, but it's not the case. Unfortunately, both energy and angular momentum were not conserved in the beta decay. The beta minus particle or electron case are found to have continuous spectrum of energy. What is that? My God. Once they observe the beta particle, which is the electron, they have different value of kinetic energy. Okay, they have almost the same thing, and this is the maximum value of the kinetic energy. So what could we predict from this result? The observed energy of beta particles are continuous, having all values up to a maximum value. It's unlike the kinetic energy caused by alpha decay or helium-42 or the alpha particle. It's discrete, right? But for beta particle, the energy is continuous, like this. It has a function in this way, right? Distribution of beta particle energies in a typical beta decay is shown like this. Okay, beta decay results in a daughter particle with a variety of possible kinetic energies. Okay, in 1930, Wolfgang Pauli proposed that because the classical physics theories were not valid, right? No conservation of momentum and energy. So Wolfgang Pauli tried to correct this theory, okay, to find more reason behind that. There should be a third particle unseen in 55. Okay, in this equation, in the beta decay process. Okay, not only the smaller or the changed element and the electron, but there should be another particle in Wolfgang Pauli expected that there should be a third particle unseen in this equation, in this process, in field 5 here. Okay, and what is that? This particle should be electrically neutral. Okay, because the charge is already symmetrical, is fulfilled on both sides of this equation. Another particle, the third one, should have no charge at all. It should be neutral in charge, so it's 0 coulomb. It should possess 0 coulomb. They say he said this particle should be electrically neutral. Okay, so that one could recover the conservation. Okay, the new expected particle should be able to explain the momentum conservation, the energy conservation. He proposed that. Yes, and later Enrico Fermi. Okay, this guy is well known in nuclear or quantum mechanics, right? This researcher, Enrico Fermi in Italy, right? Called this because he lived in Italy. He often used his languages every day, right, in his daily life, and he would call the particle that Pauli mentioned as neutrino. Okay, neutrino. Of course, the English words came from the Latin word. In Italian came from also Latin, right? They share the same root. Neutrino in Italian means something little and neutral. Okay, something which is little, which is tiny, and neutral in charge, tiny, little in mass, right? Neutral in charge and little in mass, so the mass might not be very, very high in the same scale as electron. And both people, Wolfgang Pauli and Enrico Fermi, believe there should be another new particle missing here in this process. Before that, the scientists believed there should be only two particles, the changed element and electron, but these two guys, Wolfgang Pauli and Enrico Fermi, believe there should be another third, and the third particle should have very, very small mass, right? Very tiny mass, and the charge of this particle should be neutral. There is not neither positive nor negative. In 1955, okay, this is the theory comes first. Okay, in physics, the theory comes first and the measurement came later. Its existence has been confirmed by indirect evidence. I don't know, Clyde Cowan and Frederick Linus recorded antineutrinos emitted by nuclear reactors. Okay, the one they believe or call it here neutrino is not actually neutrino. It's known in the standard model of elementary physical particles as electron antineutrino, and it's known antineutrinos. Okay, these two guys have detected antineutrino emitted by a nuclear reactor. So they made the experiments about a nuclear reaction, and they discovered the antineutrinos. And today this particle is known as antineutrino, okay, and denoted by the nu, okay, nu, nu in Greek, and with bar and with the subscript e, because it's denoted the neutrino for electron. It's called electron antineutrino because there is bar. Bar means anti, okay, anti, okay, in English. And yes, instead of 54, okay, instead of this one, okay, we would have the third particle, and the third particle is denoted here. Okay, 54 is actually incorrect. Okay, the process discovered by former researchers, by former physicists, by former scientists were incorrect. The correct one should be like this. This is the corrected version, and it has the symbol electron antineutrino too. Okay, with the subscript E means electron electron. Okay, anti bar. Neutrino is the new. Okay, the new nu in Greek letter, and the alphabet for in element symbol in like in chemistry is that it has neither proton and it has neither nucleon, right? Sorry, it has both. It doesn't have both proton and nucleon, right? And there is no charge here at all because it's neutral, right? So now this process is complete, is fulfilled. Okay, so the additional thing that take place in our story right now is the electron antineutrino, right? From this process, neutron to a proton, we have discovered the electron antineutrino by these two guys. Okay, these two physicists, they are experimentalists. Okay, they are not theorists like Wolfgang Pauli and Enrico Fermi. Okay, these two guys just create the idea, but they don't have time, or maybe they are not interested in measurement or in experimentation. Okay, to look at the whole view or two types of beta decay, we have beta minus decay before, right? Neutron to be proton, we get electron, and electron antineutrino, which is denoted by the nu with tube here, where it's the same as bar. Okay, neutron is decomposed to be proton together with electron and antineutrino. The whole process could be seen like this. Beta decay, you start from neutron. Of course, neutron has two double quarks and one up quark, and they are connected by gluon. Okay, gluon is another type of particle which are boson, right? They are used to glue quarks inside the particle to form up like a baryon, right? Baryon or proton neutron, like it, that has three quarks. Okay, this is the neutron. There are two dark quarks and one up quark. Okay, and after the conversion, one of the dark quark is converted to be up quark, and from this conversion, electron is going out and electron antineutrino is created. 2. Let's get back to the opposite process. That's the beta plus decay. We call beta minus decay, beta negative decay, because we get electron from here. But in the in a companion process, okay, in a similar process, it's called beta plus decay. Beta plus decay, what is that? It's proton that is converted to be neutron. Okay, positive charge is converted to neutral element. Neutral element, but it's not fulfilled, right? They also introduce the positron. Okay, same mass as electron, but and same charge as electron, but in the opposite way. Okay, and we get neutrino. It's not anti-neutrino. It's simple neutrino. Okay, it's the same mass as electron, but it's neutral. Okay, it's the antiparticle to this. And what is that? Because proton is made of 2 up quarks and 1 down quark, right? One of the up quarks is converted to be down quarks, and that's why they have 2 down quarks and 1 up quark. Okay, because once we have they reduce the positive charge, right? The positive in up quark is separated into positron. Okay, the whole process of this one is of the elementary here is that you have up quark here is converted to be down quark, and you know the up quark is only 2/3 a proton, okay, 2/3 charge, and it correspond to 1/3 mass of the nucleon, right? And here the quark is 1/3 mass too, but the charge is 1/3, right? 1/3 negative 1/3 of the electron, and what we got is positron, okay, which is positive 1 proton. It's like 1 proton, but it's not proton. It's smaller than proton. It's in the electron scale, and it has no nucleon because it's not proton. It looks like electron. It has nothing inside the nucleus, so there is 0 here. There is no nucleon for positron. And the next one is the electron neutrino. Okay, the electron neutrino has almost 0 mass. Is denoted by 0 proton, and the number of nucleon is of course 0. This is valid. And for the beta minus decay, we start from down quark. One of the down quark is converted to up quark. We got negative 1/3, which is the amount of the charge of the down quark, right? And compared to the proton, and 1/3 of the mass compared to the 1/3 of the atomic mass unit. Oh no, the mass number, right? Okay. Now we get up quark with 2/3. The charge increases, right? And the mass is only 1/3, or the mass number is only 1/3. And once you increase the charge, you need to reduce it by 1, and that's why we get electron here, and the electron would come together with electron antineutrino with 0 proton and 0 nucleon, and something like that. Okay. In bachelor degree, it's okay, acceptable if you cannot understand this figure. Let's consider the down quark of the neutron emits. We consider the beta minus decay. Okay, the down quark, one of the down quark, which is the red one here. This down quark, this is neutron. Okay, the bold symbol. We look at this figure from lower part to the upper part. Okay, the flow direction is from lower to upper. Okay, to upper location. We start from neutron, and you know neutron has 2 down quarks, the blue one and the red one, and up quark is denoted by the green ray here. And one of the down quark, which is the red one here, is flowing. Okay, there it's trying to transform itself, and it's release the W minus boson. The W minus boson will get out, and after that the electron antineutrino just emerges, and we also get electron from this one. Okay, other part of the you know that antiparticle will flow in the opposite way. Okay, antiparticle will go out, and yeah, W minus boson later turns to be an up quark, because dark quark changes itself to be up quark, and once we have two up quarks and one dark quark, we receive right now proton. Okay, and that's the process for 54. But one more important thing is that we have also electron antineutrino and electron. Okay, the process in 63 releases. Where is that? 63. 63 is this one. Okay, this one, the full process of neutron to proton. The process in 63 releases an amount of energy when we know that the mass of the neutron, okay, excess mass, the mass excess. Okay, the mass excess is the mass of neutron, right, on the left hand side, minus mass of proton, mass of electron, mass of electron neutrino in because the mass of electron antineutrino or electron neutrino are very hard to detect because they don't interact with other, and they don't have charge. It's very difficult to detect the electron antineutrino. Now let's move. Let's try to get the information of electron neutrino or electron antineutrino. We know that the mass of the proton is 938. Okay, mass of neutron is a little bit higher, greater than that. Mass of electron is 0.511 mega electron volt per c square. Okay, it's not atomic mass unit. It's mega electron volt per c square already. And this is the mass of the electron antineutrino, which is what we don't know. Okay, even today, the scientists or the physicists still don't know the mass of the electron antineutrino. I cannot do anything. Okay, and then you make the subtraction, you could see that the excess mass is 0.79789 plus mass of electron antineutrino. You get this one. You just approximate this one by neglecting the mass of electron antineutrino, but we know from theory that because when something is very, very small, it's very hard to compute or detect, right? But they believe that the unknown mass of electron antineutrino should be in between very, very small, right? 1 by 10,000 or 1 by 1,000. Okay, somehow it is in electron volt, not mega electron volt. It's in electron volt per second, which is very, 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 very small. Okay, which leads to released energy. Okay, we compute this one, convert 789 to be in Einstein relation times 931, right? We get somehow, oh no, it's not multiplication. It's you just multiply it by C, you get 0.789 mega electron volt. Okay, the electron neutrino. Now let's get back to beta plus process. The electron neutrino, which is denoted by nu and e, comes from the opposite direction, the opposite process to the example. In the example, we consider carbon to neutron to nitrogen, right? Here, carbon to nitrogen, but in the opposite way, the nitrogen can be also converted to carbon, okay, by throwing away one positron, which is a beta plus process. And the beta in this beta plus process, that should be also electron antineutrino so that the momenta or the energy conservation should be conserved. Okay, the electron, the neutrino has the following property: zero electric charge, a mass much smaller than that of the electron. Okay, of course, you know that electron is 0.511 mega electron volt per c square, right? But neutrino it's not million, it's not mega, it's electron volt, and it's even than number one is 1 by 10,000 or 1 by 1,000. They don't know exactly, but they should lie in this value. That's what the scientists believe. Okay, zero electric charge, there is no charge. Okay, whether it's electron neutrino or electron neutrino, a mass much smaller than electron, but probably not zero. It should not have no mass. Okay, recent experiments suggest that the neutrino definitely has mass, but the value is uncertain because it's beyond the precision of our machine. Perhaps less than 1 electron volt per c square. Here, this is what we observe: less than 1 eV per c square. Okay, its mass in the same scale as the electron, right? Is even smaller than the electron. A spin of 1 by 2. Okay, very weak interaction with matter and making it difficult to detect. Okay, and that's the electron neutrino. And the process of beta plus decay or positive beta decay cannot occur in isolated proton, according to it cannot happen like this. Okay, because if you want to split the proton into neutron and positron and electron, you need to throw away energy to proton. Okay, it requires energy due to the mass of neutron being greater than, okay, the mass of neutron is greater than proton, and you have even more mass here. It means if you want to make this process becoming true, you need to throw away the energy. It's not like the beta minus process here. In the beta minus process, okay, in the beta minus process from N to P, this one could take place because the mass of the neutron is greater than the mass of the proton. But 68 is in the opposite way. You cannot have this process easily in nature or automatically because the mass of the neutron is greater than the mass of the proton. In order to make this process becoming true, you need to release the energy to the left-hand side. You need to throw heat or any kind of energy to proton. Then this process can be true. Okay, the positive beta decay can only happen inside nuclear when the daughter nucleus has greater binding energy. Okay, once you have very, very dense nuclei, and therefore a lower total energy than the mother nucleus. Okay, that's the condition for beta plus decay, or it's a little bit different from beta minus decay. Okay, now we finish the second type of decay in what time? We still have 7 minutes, right? We're gonna exit this lecture at 11:30, right? We need to have 20 minutes break for you. 11:50 is the time we're gonna break. We take break, right? Yeah. Beta plus decay, right, is a little bit complicated because you need to have greater binding energy inside the nucleus. And you need to have the daughter nucleus should have more binding energy, right? And now we move to the third type of particle decay. Okay, we make the order for different types of decay according to the energy or the penetration ability. Okay, gamma decay, what is that? Gamma decay means the nucleus undergoes a radioactive decay. that causes alpha emission or beta emission. Okay, the gamma decay is the result after the first two steps. Okay, whether you have alpha decay that release the helium-42 nucleus or the alpha particle, or whether you just release the positron or the electron or beta particle. Once the nuclei or the nucleus were converted from any process, whether it is beta plus decay, beta minus decay, or alpha decay process, the nucleus will not get stable immediately, because after the heat, they still absorb the heat, the energy, and once the object absorb once the particles absorb the energy, they are gonna have vibration, and in that vibration, it's in the excited state. Okay, it's not in the ground state. Anything that stays stable, it means that they are in the ground state. There is no vibration. It's in the lowest energy level. That's good. But the nuclei or the nucleus from after the decomposition in alpha process, uranium or radium, they get the energy from that process automatically, and the nucleus will not be stable, will not be in the ground state. They are in the excited state. They have vibration. It's also true. It also holds true in beta decay too, right? In nitrogen or in calcium, in it's phosphorus or something like that. Right? Yes. Potassium, right? K. Potassium. What is K? K. K is potassium. Sorry. Yeah. Like in the potassium scenario, the nucleus of the potassium may not be stable immediately, not in the ground state immediately. You need to let it cool down, and this cool down will bring you the so-called photon. Okay, it's like electron move to the ground state, and the electron is gonna release certain wavelength, right? Certain light. And that's the photon, and it's the same here. Once the nucleus of nitrogen or potassium, they would need some time to cool down and remove the vibration. The removal of the vibration will give us the photon. Okay, and that photon is called gamma energy, gamma ray. Okay, it's like the light we observe with eye, but it's in the different region, it's different frequency, different wavelength. Okay, and it has much more energy. It has a different property. We use it somehow in medical purpose. For example, if we wanna find or investigate where the cancer exists in our body, we're gonna throw away the element that can produce gamma decay, and we use the any plate to detect the gamma from that one. Okay, the gamma decay occurs when the daughter nucleus undergo another decay to lower energy state, perhaps to the ground state, caused by proton and neutron in the nucleus that move from higher energy level to a lower one, resulting in the emission of extra energy in terms of gamma ray photon, or sometimes it's known as the gamma. Okay, it's a kind of photon, but it's known specifically gamma. Okay, because photon can have different region, right? It's the light region, ultraviolet, infrared, blah blah blah, right? But gamma is the region in photon, and the energy from gamma ray here is from 10 kilo electron volt to 5 mega electron volt. So it's considerable, right? Yeah, it's quite high. The gamma decay could be written in chemical expression like this is the same thing, right? You start, for example, from the alpha decay, you have radium, and you got radon 222, right? 226 to 222, 88 to 86, and we get helium particle. But we leave the star symbol here on the right hand. It's not conjugate in complex, right? It's the excited state of the nucleus of radon, and the excited state of the radon nucleus is converted to the ground state, and this excited state will bring us the photon too. Okay, will give us also the photon. Okay. So that's the whole thing we could get. Yeah, we could not do anything. Yeah, it just emits the gamma from this unstable nucleus state or the excited state. Let us consider the total released energy at 4.871 mega electron volt or 4.685 mega electron volt from 69. Okay, you start from radium, right? Radium 226 to 88, and once this radon emits the alpha particle. Okay, there are two ways. The first way is that the radium nucleus just release the alpha particle and it finishes. Okay, you got the alpha particle and the radon nucleus in the stable version, right? In the stable state. And in another way, you get radon. You start from radium and you get radon nucleus, but in the excited state with the star symbol here. And the energy difference here is only 4.685, but the complete process has the energy released by 4.871. Okay, and in this process, when the nucleus of the radon is in excited state, it's gonna need some time, and it will, when it's cooled down, you will get the radon nucleus in the stable state, but it will emit the gamma ray. The gamma ray is the difference between the typical process and the unstable process here. So you could find the difference, and the difference is 0.186 mega electron volt. Okay, and that's the 0.186 mega electron volt for the energy of the gamma ray. Okay, I know that gamma decay. Sorry, the time is over. I'm gonna finish soon, right? Okay, we finish this page and the lecture will be closed soon. Note that the gamma decay results in a change in neither the mass, so mass number A doesn't change, the atomic number Z also doesn't change. Okay, let's talk about the possible example of the gamma decay. Gamma decay that happens in nature is, for example, from boron to carbon. Okay, boron 12.5 to carbon 6. What does that mean? It means neutron is converted to proton. This is the beta minus decay. Okay, the process. Okay, you see radium to radon, right? And you get gamma ray. But for beta decay, you can have also, for example, boron 12.5 to carbon 12.6, carbon, typical carbon. But this nucleus is not stable. It's carbon with star. And the thing is that you get the electron, right, which beta minus particle, and you get electron anti-neutrino. And after that, the nucleus of the carbon 12, which is in the excited state, will be cooled down to the ground state. And after, in this cooling process, you get the gamma ray too, right? Yeah, and the human use the gamma from this process for some purpose like medical diagnosis for medical care purpose or something like that. Okay, so that's the whole thing for gamma decay, and it's time for you to have the homework. I don't know the 9 or the 10 homework to you, but the homework for today is something about beta decay to M605. Okay, homework, I don't know what is that homework for M605 is beta decay. Okay, there is no calculation in gamma decay. Homework for M605, so it's 14.01.2022. Okay, and we arrive at this page, right? Gamma decay 14. Okay, we're gonna start next week 14.01.2022. Okay, see you next time. See you next week. Hope you enjoy your weekend. ก็วันนี้ก็จบเพียงเท่านี้นะครับ605นะครับการบ้านก็คือทำปัญหาเกี่ยวกับเรื่องเบต้าดีเคนะครับเดี๋ยว create ใน Google Classroom ให้นะครับแล้วก็ตรวจการบ้านเพิ่มนะครับครั้งหน้าพบ carbon dating. If you have any questions, just let me know. Okay. Otherwise, we're gonna exit our lecture right now. Okay ครับสวัสดีครับบ๊ายบายครับ